Thanks, Luis. I heard about the JQI first as a graduate student. Somebody I knew who's now here, Jake Taylor, came here. Although I didn't know what the JQI was, nor did some of our graduate students, so we ended up calling the JQI the Jake Quantum Institute. I think by now, many, many more people know about this, this nice place, and I'm very happy to be here as a fellow. Last year I was on the job market, and when you go on interviews, you have to meet with people outside of your area. And one of the complaints I got from people outside my area was that people in condensed matter physics have a very short attention span. I think that's sort of true. Up until the turn of this century, we had a material that sustained us for about a quarter century. That was two-dimensional electron gases and at the interface of gallium arsenide and aluminum gallium arsenide. And I think something like 50,000 papers came out of that one material system, something absurdly large. And so in that sense, we certainly don't have a attention problem. But over the last decade or so, we've kind of switched materials rather rapidly. We've gone through nanotubes, graphene, topological insulators, all pretty rapidly. And I would say without really getting to the bottom, or yet, we have not gotten to the bottom of the physics in these materials. But what we have latched onto as a community, I think, is the idea of emergent phenomenon. And what I mean by that is we take a collection of electrons, we put them together, and what we get out from these collections of electrons is very different from the individual particles that went into making these material or this system. I'm going to try to highlight what we're looking for in these systems by talking about Majorana fermions. But it's funny that Luis brought up Blas Cabrera. I was looking for neutrinos as an undergraduate. I'm not so far from looking at neutrinos anymore. And so it's interesting how my career has come full circle. The first talk I went to as a graduate student was by Paul McEwen. It was a big physics colloquium. And in order to excite the masses about this particular system, Paul started making the analogies between carbon nanotubes and massless neutrinos. And it turns out they have very similar band structures. And he started talking about helicity and neutrino oscillations. But he kind of stopped himself as he rolled down this hill a bit because, as he put it, he didn't want to take the analogy too far. But a natural question that kind of arises from where Paul was going with this is, if we have band structures that look like something else in particle physics, how far can we take the analogy between, say, electrons in nanotubes and, say, massless neutrinos? I don't think we really quite know yet, but something I think very interesting has happened over the last few years, and that's graphene. And it turns out that, while there might be analogies between electrons in nanotubes and other particles that may or may not exist in nature, the unique band structure of nanotubes, and in this case graphene, have actually measurable effects when you do electrical transport measurements. And I think people knew this, especially theorists have known this for a long time, but it really took graphene to get the experimental community to latch onto the idea that the unique band structure of graphene can actually be seen in just making measurement of the current versus the voltage. And the first part I'd like to point out where this existed, this was in the quantum Hall effect in graphene. You may know that in conventional two-dimensional electron systems, the density of states look like harmonic oscillator states. But in graphene, the situation is different. Because of particle-Hall symmetry and because there's a zero energy state at B equals 0, there's this zero energy Landau level that exists even when you apply a magnetic field. And this zero energy Landau level causes the plateaus, the value of plateaus that you measure in the quantum Hall effect in graphene to be different. The next part where I think this came up was inclined tunneling, something that was put forth in particle physics many, many years ago. And this is the unit when an electron or a particle approaches a barrier. If the barrier is twice its rest mass and height, you get unit transmission through that barrier. So for something that looks like massless particles, you should get unit transmission for any value of that barrier, and we've actually seen that in graphene. So it's interesting. You can start to actually play with the band structure, something that's very different from what I would call conventional two-dimensional electron gases. And I've shown here the band structure that's pretty correct for almost all materials that you might work with that we have before, say, quantum materials. There's a S-like conduction band. There's a P-like valence band. Often that P-like valence band is split by spin-orbit coupling. But the dynamic properties that arise from this band structure are very similar to electrons. They have the same dynamic properties, mass, charge. The mass is slightly different always, but you still get electron-like excitations. More recently, though, we've moved on to more exotic band structures. I mentioned graphene that has a linear band structure. Just after graphene, something that are called topological insulators, which I'll talk about a little today, where in addition to a bulk valence and conduction band, there's these interesting Dirac-like surface states that exist in the bulk band gap. And more recently, people have started to look at more and more exotic materials, something called spin liquids, where because of the geometric arrangement of electrons on this lattice, there's a frustration. It's hard to satisfy any antiferromagnetic interactions on this frustrated, this is a Kagame lattice, but any sort of triangular-like lattice. It turns out the excitations of this kind of system are very interesting, arising from arising from this emergent sort of Z2 scalar field. I think the latest ideas for what the electrons will look like is something called bosons, which I've never even heard of. But it's interesting, as you go from graphene, you can start to increase the complexity and think about more and more interesting particles you can measure in the solid state. And then you can ask, well, when you get down to very low temperatures, what sort of properties of the ground state do you have? In a conventional two-dimensional electron gas at zero magnetic field, the ground state properties are either a metal or insulator with some small caveats in between those two phases. In quantum materials, you can actually start to think about playing with many different ground states. This is the ground state behavior for something that has strong electron-electron interactions and also strong spin-orbit coupling. And you can think about moving around this diagram with simply a gate voltage. The electron-electron interactions can be changed by the number of electrons you have in the system. This lambda parameter is the spin-orbit coupling, which can also change for the electric field by changing the confining potential. But I think it's exciting. It definitely is a step up over the very basic phase diagram that you get from non-interacting electrons in conventional two-dimensional electron gases. So some of the phases that were talked about here were topological band insulator, topological Mott insulator, gapless Mott insulator. Looking at the phase transitions between all those states, I think would be a very interesting thing to do. So we've kind of gone down the complexity of band structures in these systems, but I got to say that experiment hasn't really caught up with the evolution of more and more interesting band structures, transport especially. And the main problem is materials in origin. Not to blame JP or anybody like that, but the problem is that you get these devices, you make electrical measurements, and you get something that looks like this. And it really doesn't matter what these parameters are. This is a gate voltage, this is magnetic field. But you see something that looks interesting. There's lots of peaks and lots of wiggles, and it often turns out that those seemingly interesting peaks and wiggles aren't anything. And this is really due to disorder. The mobility in these systems really pales in comparison to what we have in say, gallium arsenide, aluminum gallium arsenide. But I gotta say there's hope. And to illustrate that, I just want to show you what the quantum Hall effect looked like when I took it as a graduate student in graphene. You can see that this spacing, this atypical spacing of the plateaus at 2, 6, and maybe 10 e squared on h. Those are the signatures of graphene arising from this interesting zero Landau level, zero energy Landau level. But aside from being relatively clearly able to see these peaks, these steps, the quantization isn't that good, and there's really nothing going on between, say, 2 and 6. And notice I highlight the nicer electron side. Even on the hole side, it's a little not so good. But so this was 2008, I think. This is data we took at the magnetic field lab in February. This is also graphene. This is a zoom in of, say, the quantum Hall states between, this is in gate voltage, but here's 2, and here's 6, here's 6. You can actually see all the degeneracy split. So you see plateaus, or this is peaks in the longitudinal resistance. You see peaks at, say, 3, or just before 3, just before 4, just before 5. And actually, if you go up in field, those peaks are split by the fractional quantum Hall effect. Anyway, this is just to illustrate that although materials aren't that great in these more exotic and these more exotic things like topological insulators, we're definitely riding the so-called punctuated equilibrium of materials progress, which in graphene has actually been rather fantastic over the past 5 years or so. So I said we want to look at maybe excitations of an electron C that are different. What do we look for? How do we know what to look for? And I think it's kind of useful to go back and look what I would call like the rule 0 of condensed matter. What happens when you put a collection of particles together? We know this sort of defines 2 classes of materials that you're very familiar with, bosons and fermions, and what happens to their wave functions when you interchange 2 particles. For bosons, you get the same wave function. For fermions, you get the same wave function modulo a minus sign. But these 2 rules of quantum mechanics or condensed matter physics really dictate the behavior of collections of many of these particles. This property is responsible for Bose-Einstein condensation, or allows for Bose-Einstein condensation. This creates Fermi seas, Fermi spheres. So it would be interesting to take this sort of rule 0 and see what else you can get and investigate those more unique exchange properties in the solid state. And there's another class of materials that known to exist in 2 dimensions called anyons, rising from the fact that when you exchange 2 particles, you can pick up any phase, just as a prefactor to the wave function, e to the I phi. This is called abelian statistics. But there's a whole other class of materials that are perhaps more interesting and maybe more useful when one starts to think about what we want to do with these quantum materials, and that's something that has non-abelian statistics, meaning that when you take 2 particles and interchange them, you get an entirely different wave function altogether, not just some similar wave function with a phase factor. And I should point out that, as you go down this list, these particles are more and more difficult to see. I think, bosons and fermions people know a lot about. These anyons, I think before Majorana physics, I'm sure there's other fields or systems where this was known, but the only real system that I knew that kind of contained these properties were in the fractional quantum Hall regime. And in particular, this non-abelian statistics, there's a particular fractional quantum Hall state, the 5-half state, that should exhibit these non-abelian statistics. Although, despite the really good quality of materials, it's very hard to see that 5-half state. So that kind of forced people to look other places for something that might have unique interchange properties. And this leads us to the Majorana fermion, which, as Charlie laid a little bit of the groundwork for me last week. But just very quickly, Dirac solved this equation for relativistic spin 1/2 particles. And in doing so, he created a set of these gamma matrices, which have both real and imaginary parts. Some 8 years later or so, Majorana solved this equation, and his set of gamma matrices were all imaginary, which makes this equation real, this part of the equation real, meaning that the wave functions or the fields that you get out of this solution have to be real too. And this has the sort of tagline byproduct that the antiparticle is the same as its particle, which is not true in the direct solution to this equation. Formally, what this means, I guess, is that the fields that you get from solving the Dirac equation, they have to be real and imaginary parts, so they have essentially 8 degrees of freedom. When you switch to the Majorana version of this, which is called acquiring a Majorana mass, you basically have 4 degrees of freedom for the various fields. So going back now 30 years, a little more than that, people started thinking about, initially from a Hamiltonian perspective, but more recently from a materials perspective, how do you see these things? What do you need to see these things? What are the properties of a system that you would need to observe Majorana fermions in? And the first place I think where this really came about was this work by JQI and Rossi many, many years ago, which basically says that if you take the Dirac equation and you add some scalar interaction, something like, they even said this in their paper, something like a superconducting interaction, you can get Majorana 0 modes in this system. Building off that work, there was 2 sort of condensed matter theorists, I don't know what Kitaev likes to be called, putting forth material systems where you might actually be able to see these 0 energy Majorana modes. Kitaev proposed a one-dimensional superconductor. Reed and Green talked about taking the fractional quantum Hall effect and adding pairwise interactions. Both of this you get Majorana modes in just from those interactions. Although I would say these 2 proposals, although interesting, are very hard to achieve experimentally. More recent work have really put forth devices and materials that we know how to work with, we know how to make, and that at least in theory should have a Majorana mode in them. One is by Charlie Kane and Liang Fu. I'll be talking about this structure today. But before we go on, I want to talk about probably the most experimentally studied and what the community has the most faith, I would say, in seeing Majorana fermions, and that's a proposal set forth by 2 people who are here and who are JQI fellows, Shankar Dasarma and Jay Sao. They basically propose that if you take a semiconducting quantum well, you couple it to a superconductor, and you add a magnetic insulator, something that breaks the Kramers degeneracy, the K = 0, spin up, spin down degeneracy, you can get a Majorana mode in that system. And building on this work, there have been a series of more specific, more experimentally driven theoretical work, that's what I would call it, and that's looking at similar systems but taking a one-dimensional system with strong spin-orbit coupling. So what strong spin-orbit coupling does in one dimension, it splits along the K axis, the spin-up and spin-down parabolic bands. And to get from here to Majorana, just simply stating the recipe, you add a magnetic field or a magnetic insulator, something that breaks this K = 0 Kramers degeneracy, and you add a superconductor. So these are all things we know how to do in the lab. We know how to apply magnetic fields, and we know how to build devices that are coupled to superconductors. And I think 2 years ago now, Leo Kouwenhoven's group did this, and they measured something that looks like this. And there's a lot going on in this graph, but where you point to, I think this is one of the benefits of this work, is you can point to where the Majorana should be, and you can see that at 0 field, so this is as a function of magnetic field, this is the bias you apply to the device, and this is the conductance along the y-axis. At 0 field, you don't see anything happening at 0 bias, but as you apply the magnetic field, as you open up this gap at K = 0, you see the Majorana mode form. So this peak at B = 0 is what you can point to as being Majorana. That was 2 years ago. And I think since then, as people often do with very good experimental work, they are not necessarily good, all this is good, but interesting experimental work is they start to pick it apart. And I'm not going to make a stand about whether this is or isn't Majorana, but there are some interesting things people have noticed about this data that point to it maybe not being Majorana. So this is now a two-dimensional plot of the bias and the magnetic field. So this is all these slices from the last graph kind of laid on top of each other. And out of the board is conductance. So if you look at B equals 0, you don't see a peak in conductance. But then as you apply a magnetic field, you start to see a peak. But something else happens when you start to see that peak. You can see that these peaks out here, which are the peaks in conductance associated with the superconductivity, they start to collapse at about the same time the Majorana peak comes up. And what this might be is that, in addition to an energy scale associated with the superconductivity, the induced superconductivity that gives rise to Majorana fermions, there's a lot of other energy scales and things going on in this device that might give rise to a peak at zero field. One of them is the Kondo effect. And so one critique of this particular graph would be that as the superconductivity starts to die off as you apply this magnetic field, the Kondo peak, the energy scale associated with Kondo now becomes the dominant energy scale. And this peak you see at zero bias is associated with Kondo, not Majorana. So then the question is, if this system is ambiguous in the sense that there's a lot of energy scales associated with this zero bias peak that may or may not be Majorana, are there material systems where we can make the signature of Majorana more clear? And the answer is, well, not yet, but maybe soon. I'd like to just highlight some of my work from two systems where I think hold a lot of potential in really knocking down whether Majorana exists or doesn't exist in these systems. One is a topological insulator Josephson junction. And it turns out in this setup, theory has shown that there's no real limits on the size of the topological superconducting gap you can create. And that gap is immune to disorder that we all know exists in these devices. This is not true in the one-dimensional case that I just showed. That has a very sensitive relationship with disorder. The other is looking at complex oxide materials. I'll talk about perhaps that we've seen the helical metal state. And a helical metal state is just the spin-orbit split bands with the k equals 0 degeneracy removed. So if I can go back just to show what that is real quick. If you remove the degeneracy here, you have spin down electrons that are moving to the left and spin up electrons that are moving to the right. So there's a correlation between spin and the direction of propagation. That's what I mean by helical metal state. The other thing that might be easier in this system is that we're using, as I'll show, a material that can be made a superconductor on its own. And one of the problems with the one-dimensional work is that it's very hard to couple the superconducting state into the material. So maybe this will allow you to both couple in superconductor and as I'll show in this talk, maybe add that magnetic insulator interaction that allows you to remove the k equals 0 degeneracy. Okay, so we'll start with topological insulators first, just as a very picturesque view of what a topological insulator is. They're materials that have small band gaps and so large spin-orbit interaction that when you split that p-like valence band, the bottom of the conduction band actually becomes so high in energy, it overtakes the valence band overtakes the conduction band. So you have this, what we call inverted band structure. And if you take, if this material would exist on its own and never interface with any other material, the properties of the system would look very similar to a conventional two-dimensional electron gas or three-dimensional electron system. but it's when we interface the system that really at its heart has a different topology than what I would call a normal band insulator like the vacuum. It's when you interface these two materials, you actually get an interesting surface state. This surface state has a Dirac-like linear band dispersion, and also has spin and momentum tied together. So it's interesting. But you need something that is a heavy element, so that has strong spin-orbit coupling, and also has a small band gap. And one of the materials systems that this has arisen in is bismuth selenide and bismuth telluride. Very large, high-quality crystals of these can be grown. JP's grown these and some variation of these here at Maryland. And if you look at these materials in something that's very surface sensitive, you see this very nice picture where you can see, in addition to the bulk conduction band and valence band, there's this surface state that has a linear dispersion. Further, they've shown that, that along this arm, if you look at this particular arm, it's been polarized. On this other arm, if you look at the other side of K, minus K, it's been polarized in the opposite direction. So very nice ARPAs and STM work. Anything that's surface sensitive, topological insulators look very good in. In transport, not so much. And the main reason that people are still working on, I think, are that there's a large gap, but they're always so doped, mainly due to selenium vacancies, I think, for bismuth selenide. They're so doped that the bulk still contributes to the transport. And you can see this. You look at the Fermi energy here. You have the surface state, which is at the Fermi energy, but you also have this very large bulk conduction band. So when thinking about measurements in the system so far, you always have to think about the bulk as being part of what you measure in transport. So what are we going to do with this material system? Bismuth selenide, you'll take a topological insulator and you'll put a superconductor on top. And if you can make this interface between the superconductor and the topological insulator good enough, some of the superconducting properties will leak into the topological insulator. And if you put two separate superconducting leads near each other, the leakage of the two superconductors can overlap, and you can actually pass a supercurrent through here. But what they've shown is that, well, in this region where you induce superconductivity, you actually impose on the superconductor and the topological insulator. You impose this particle-hole symmetry. And because the topological insulator has a zero energy state, and it's when it's all by itself, that zero energy state stays pinned to zero once you apply the superconducting leads to it. And if you look at the excitation energies inside this Josephson junction, for a particular phase difference, superconducting phase difference between, say, this lead and this lead, you do get a zero energy state, and this zero energy bound state has properties of Majorana fermion. I should point out, unlike the work by Kouwenhoven, where it's a one-dimensional system, and the interface between that one-dimensional system and the superconductor is a zero-dimensional object. Here, what we have is a three-dimensional, or we have a two-dimensional interface on top of a three-dimensional material that produces a one-dimensional line of Majorana fermions. So what we actually have here is a collection, a wire of one-dimensional Majorana fermions. At least in theory, that's what we have. Okay, so we make these devices. I thought I had a picture of them somewhere. Don't. These devices aren't easy to make. You actually have to put these two superconducting leads quite close together to induce the topological superconductivity in this region, and then measure a supercurrent. You have to get this to be 20, 30 nanometers apart, which we can do. And when you do that, you measure something that looks like this. This is the current you apply to the device, and this is the voltage that you measure. And you can see for small values of current that you apply, no voltage develops. And at some point, you hit a value of current that the voltage jumps up and moves linearly away from that point. This is a very typical behavior for a Josephson junction. Usually how you quantify the behavior of a Josephson junction at DC is you look at the product of this value of current where the resistance jumps up, that's called the critical current, times the normal state resistance. And in conventional Josephson junctions, that product is related to the superconducting energy gap that you induce in the sample. What was kind of interesting and new in this device, and I would say something that we still don't really have a good hang on what's giving rise to this, is that this ICRN product, which should just be a function of the energy gap you induce in the system, has some geometric dependence, which our initial thinking was that it has something to do with the length of the Majorana wire. I'm not sure that's relevant, but anyway, we observe something that's anomalous. And even when if you go out and take data from other people's work on these junctions that have come since then, these 3 different works here, you can see that when you use bismuth selenide or bismuth telluride and you see this sort of overall 1/W trend. I don't know what to say about this. They made a device and didn't observe superconductivity. It was a very wide device, but I don't know that you should necessarily include that in the plot. Okay, so we noticed that sort of geometry dependence to this ICRN product. That was one interesting thing we saw. The other came about when we started applying magnetic fields and looking at the response of the Josephson junction. Typically what you see is something that looks like this. As you pass a single flux through the area of the device, because of the Aharonov-Bohm phase you get around here, you can actually cancel out the supercurrent. And so you see this Fraunhofer pattern. The scale of the Fraunhofer pattern is set by the device area. The device area is just the distance between 2 leads plus how much on each side the magnetic field penetrates the superconductor. And that this Fraunhofer pattern arises when you have this conventional current phase, the Josephson relation. So as we know, or I didn't know, but after I started this project, as I learned that the current phase relationship for a system that has Majorana fermions is different. I don't know if Victor is here. Victor. One of the early works, probably still my favorite one on this topic, about what happens when you have unconventional pairing in superconductors to the current phase relationship, was done by Victor and colleagues. But that you get this sort of fractional Josephson effect, where this current phase relationship is now 4-pi periodic. So if we add that into the Fraunhofer pattern, does that change it? Yes, it changes it in a trivial way. The first 0 is at 2 instead of 1. But if we think about how Majoranas might affect the junction, I should have put a slide on this, but when you're thinking about how, I'll just skip that. Let me just say what the experimental data is first, and then I'll talk about how Majoranas might affect this Fraunhofer pattern. Here's what you get for the Fraunhofer pattern of Josephson junction. And this isn't just one device. We measure many devices that look like this. In black is if you take the device area and you include the penetration depth of the superconductor, you should expect a Fraunhofer pattern that looks like this. You can see 2 features that are important. One is that it's substantially narrowed with respect to this expected Fraunhofer pattern. And then the other thing, perhaps more interesting, is that you have this first 0 is elevated off, it has some finite critical current associated with it, whereas the second 0 and maybe the third 0 don't have this. For the reduction of area, not area, but with the magnetic field, I think we can sort of explain that by conventional means. Conventional means that we didn't appreciate at first. It turns out when you put a superconductor on a topological insulator, it changes the property of a superconductor. And it changes the property of the superconductor that in ways that you wouldn't expect from, say, if you put it on a metal or a semiconductor. We don't really understand that, but You take a superconductor, you put it on a topological insulator, it actually kills the superconductivity much faster than it should, based on the density of states of electrons in the system. Now for this first zero, I should have mentioned at the outset, a lot of things can make your Fraunhofer pattern go bad. We spend a lot of time working through those various ways. You can get elevation of these zeros away from zero critical current, but usually what happens is that all of the dips are all elevated off. This switching between up and down, and hopefully as we do more work, we might see another up here and another down here. When you have a single flux through the device, this is when Majorana physics should dominate. So one of the sort of working theories about this is that this peak here is really related to the current that's being contributed by the junction from the Majorana fermion. But I don't know. We haven't worked out the details of that yet. That's ongoing work. So to get this Fraunhofer pattern, we had to propose a funky current phase relationship, and one in which at pi and 3 pi, we actually had peaks in the current phase relationship. And we can kind of emulate this property where you get a narrowing of the first central peak and an elevation of the first low or first zero. If you do that, we then looked at these samples with a squid, and we saw nothing interesting about the current phase relationship. Although I don't know, this is a DC measurement, and for reasons that have to do with quasi-particle poisoning, it might be that measuring these samples at DC or higher frequencies have an effect on what your current phase relationship will be. I should mention that more recent work by Dale Van Harlingen at University of Illinois have actually seen similar things to what we've seen and proposed similarly a peaked current phase relationship where every time you are at pi and 3 pi, you get a peak in the current phase relationship that's related to Majorana. But we don't know. We really need to understand a lot more. I mentioned that when you put a superconductor on a topological insulator, the properties of the superconductor change in ways that we don't understand. I think before we can really go forward, there's a lot of groundwork that needs to be laid in these Josephson junctions before we can really identify whether we have Majorana or not. Okay, so that's topological insulators. I want to talk a little bit about complex oxides, making nanoscale devices in strontium titanate. This work, I didn't mention it, but the last work has been published in PRL. This work is under review at Nature Physics. The first reviews are pretty good, so I hope to see this in print soon enough. But before we get to really tackling complex oxides, we need experimental tools to deal with the very high electron densities that you need. You might know that for a Mott insulator, you need half an electron per unit cell. What that translates to for a two-dimensional system is a density around half, or 5 times 10 to the 14 electrons per centimeter squared. And we want to play with that number of electrons with the gate voltage. That's basically one of our experimental knobs we have to look at the phenomena we can see. And if you look, conventional gating, by which I mean like a field effect setup where you have your two-dimensional electron gas, you have an insulator, and you have a metal. You capacitively couple that metal to the two-dimensional electron gas. Conventional gating can only get you so far before you usually have dielectric breakdown. So for very nice films of alumina grown by ALD, you can get about changes in density of 1 times 10 to the 13th per centimeter cubed or squared, which is not enough to really deal with this correlated phenomenon that exists in complex oxides. So we turned, as many groups did, to something called ionic gating. Ionic gating has been known for quite some time. I think the first transistors that were proposed, they were thinking they would actually use an ionic gate rather than a conventional metal gate. But what happens in an ionic gel or ionic liquid if you have a gate in a device? If you apply a voltage to this gate and you have a collection of mobile ions in the system, you can drive those mobile ions to the surface of the device. And this is really where you gain in ionic gating as compared to conventional gating. You can bring those ions right to the surface so that the electric fields that they generate are very strong. And they're so strong, in fact, if you put too much voltage on this gate, you can actually start ripping out atoms from your device. So we're talking about very, very strong electric fields. As I showed on the previous graph, you can sort of get 1 or 2 orders of magnitude more density swings compared to conventional gating, and you can create very large electric fields. I think both of which will be interesting as we start to look at high density, high spin orbit interaction materials. But for today, we're just going to stick to strontium titanate. And one of the first things that we did with this system was we were able to start with an insulator, turn it onto a metal, and as we continued to turn up the voltage, we were able to induce a condo state where there seemed to be localized magnetic impurities that were being screened by the itinerant electron C. I think this is the first time in 2 dimensions that you've been able to tune from an insulator to a metal to a condo state. And this work was really able to start to explain some of the emergent magnetic properties that people have seen in both STO and at this interfacial system, LAO-STO, which is basically a way to get a 2-dimensional electron gas in STO. But what I want to talk about today is this hybrid approach we've started doing to create nanoscale devices in STO. And I'm going to talk a little about the interesting transport properties that we've seen in the system. And what we've done is we've actually combined the old and the new. We've combined the ionic gating with conventional metal gating. And what that's allowed us to do is actually have very precise control over where the ions go. This is more a lithographic technique, I think, than anything else. It may have some future use if you need to make devices out of this. The ions are very slow. They don't make good RF devices, so creating these hybrid structures where you induce an electron gas and then you change its properties quickly with anyway, that's down the road. But what we use this for is more lithographic. And so just to illustrate how that works, we have the ionic gel. Before we put the ion gel on, we actually pattern this metal gate on top of it. And when you apply the voltage to this gel, you drive the positive ions here, but this kind of screens away the positive ions. So what you can do is you can create a 2-dimensional electron gas here, a 2-dimensional electron gas here from the ions, and then you can, by varying the gate voltage on this gate, couple these 2 electron gases. So we're going to look at the properties of what you see in these structures today. So what do? So this pink region we've created with the ionic gating. This gives a little bit of stats about the material that we create with the ion gel. The bulk density is about 0.5 × 10⁻⁴ per centimeter squared. If you dope strontium titanate that high, it becomes a superconductor. I think strontium titanate is the first semiconducting superconductor, which is an exciting knob to play with, and I'll talk a little bit about towards the end of the talk. So we put the ions in place. We have to do this at room temperature because at low temperatures, the ions are frozen out. So what you do is set it at room temperature, you cool the device down. The conduction is set in these pink regions, and then we're going to look at the transport properties over voltage biases and measure the current that flows through this device. We're going to measure the current that we set up in this device as a function of this gate voltage. And if you look at it, when the gate voltage is small, so say 0 to 1.6, 1.7 volts, you don't get any conduction, basically because the strontium titanate underneath this is still insulating. But as you turn up the voltage and start to bring in electrons into the system, you start to see conduction. And if you take a look at that conduction, so this is just a slice right here through 0 applied bias voltage, you see steps in conductance. And those steps occur at 1 and 2 E squared on H. There's something funky going on here. And I would say when we first saw this, we were like, you get wiggles in conductance all the time. The fact that they happen to be around 1 and 2 E squared on H is nothing exciting. But when you start to look at the bias spectroscopy, the voltage bias spectroscopy. In addition, so this is the DC, so this is basically slices of this thing as you approach this turn-on point. At zero bias, you see a collection of the current peaks around 0, 1, a little bit at 2. It's a little less than 2 here. But what's interesting is that when you go away from zero bias, you see these half plateaus. So there's a collection around half E squared on H, more so, a little less so, around 1 E squared on H. And this comes when you actually have quantum confined levels and you move. So what the voltage spectroscopy does is move up, down the Fermi energy of the leads. When you move into a region where you have 2 confined levels in your quantum point contact, you get this half E squared on H plateau. And so I think this is very convincing that this is, in fact, quantum point contact-like behavior. And say that we've seen this in other devices now. So you can kind of rule out, I'll talk about that in a second, you can rule out contact resistance. So what's going on? We just had a bar here. So why are we seeing quantum point contact behavior? Well, as I said, when the voltage is low, there's an insulator between the two, and you don't see any conduction between this superconductor and that superconductor. I should say that the bias spectroscopy I showed was with a little magnetic field applied, so this wasn't a superconductor, it's just a metal. When you turn up the voltage and you create a metal, and then you just have a metallic behavior in this regime, what I didn't show, I won't show today, is that we've actually studied the superconducting spectroscopy of this superconductor metal superconductor system, and it's interesting in its own right. But there's a sort of in-between percolation regime that arises because of disorder in this sample. So as you turn up the electron C, what's going to happen first is you won't get a direct transition to the metallic state. Actually, puddles of electrons will start to form that kind of are confined to the disorder potential. And in a few devices, not all devices, we see that as these puddles grow larger, when there's a point when one of the bigger two puddles kind of connect, or bigger three puddles connect, and you have this very small constriction. And so we think this small accidental constriction is what's giving rise to the quantum point contact behavior. It's something that we can and in the future will control, but for now, we in some devices we get what looks like one connection. In some devices, we actually get what looks like two connections. You can see sort of two parallel quantum point contact-like behavior. So, okay, why that's probably why we're seeing these plateaus in conductance. The plateaus, however, were at 1 and 2 E squared on H. And if you look at a electron gas where there's a degeneracy between spin up and spin down electrons, you should see plateaus at 2 and 4, 6 E squared on H. So why are we seeing these half plateaus, these at 1 and 2 E squared on H? Well, one is that you have poor contact resistance. We are able to rule this out for two reasons. One is that we've seen this behavior over many devices when we see the one-point contact-like behavior, and it would be rare that they all seem to have the same contact resistance. What we've done in the superconducting regime is actually probed that contact resistance, how well coupled the system is at that interface, and they're actually very well coupled. And so we've been able to sort of rule out contact resistance as a source for these half plateaus. Something else that's perhaps more interesting goes back to thinking about what ground states you have in strontium titanate. And we've actually done work on this, and other people have too, not just us. And if you look at the density behavior of the low temperature ground state of strontium titanate, one of the things that's been known for a very long time is that there's a superconducting dome related the TC to the density. In addition to that, us and other people have seen above that superconducting dome, they've seen ferromagnetic-like behavior. And for a range of densities, it turns out that both superconducting and ferromagnetic correlations exist. Which is kind of strange because they're seemingly opposite, at least in a conventional superconducting perspective, opposite things. Superconductors pair like this, ferromagnetics pair like this. So we don't really know what's going on at this interface or at this coexistence place. But one of the theoretical proposals building on this work has looked at a possibility that there's your itinerant electrons are pairing in a superconductor, and that there's a whole collection of electrons that aren't mobile. Those are ordering themselves ferromagnetically, and if that were the case, if we had mobile electrons that were in proximity to a ferromagnetic strip of immobile electrons, we would get a broken degeneracy at B equals 0, and we would observe these half-integer plateaus. So it's interesting because actually this superconductor plus ferromagnetic situation is exactly what we're looking for Majorana physics. We need something that has superconducting correlations and that breaks the B equals 0 Kramers degeneracy. And the fact that these are all integrated into one system, and a system that you can sort of tune throughout the device which ground state you have, might be a very interesting way to try to get at these Majorana fermions. Okay, so just to summarize, I've told you a little bit about quantum materials and the emergent phenomena therein. I've shown you two material systems that are in their infancy, to be the most judicious, I think, are in their infancy, but do have a very strong potential for being a system where interesting emergent phenomena can give rise to novel ground states that I've indicated in complex oxides, but maybe a very nice way at getting at Majorana fermions as well. And so I hope today I've kind of shown you that although we've been bouncing around material system to material system, we've definitely locked on a few ideas of what we want to do, and I hope you guys can stay tuned for the next few years as we really hash out those ideas and see what comes about from these materials. With that, I'll put up my collaborators on the various systems, and thank you for your time. I didn't mean to promise that, but
Well, would you say a little more about
that? What's promising about that is for STO, for example, is that you have the ability to tune in and out of the superconducting state with a gate voltage. So you can look at phase transitions between a metal and a superconductor, something you can't do in, say, aluminum when it goes below the superconducting transition, because it's a metal that has 10 to the 23 atoms per, and that's just too hard to actually gate. There's too much screening, you won't change anything. And so you need to look at systems where the densities are small enough that you can actually start to think about making changes in the density, and then you can go through and kind of do these, what is the quantum phase transition between a metal, No, yeah, but it's quantum in the sense that you can do it at 0 temperature, just by changing the electron density.
But is it quantum in the sense that it's driven by quantum fluctuations rather than by thermal fluctuations?
Yes, it's 0, yeah.
Okay, so that's a very different kind of thing.
Mm-hmm.
That's cool.
Concerning this last part, are there any ideas on how to clarify the nature of this superconducting ground state? Like, I don't know, for instance, for E waves or conductors, you can think of interferometry.
Yeah, there's also tunneling too that tell you something about the strongest. If this were an unconventional superconductor, the strongest theoretical description, I think, is an FFLO type state. And so looking at the tunnel spectroscopy as a function of parallel field or something like that would give you indications whether it is, say, P wave type pairing rather than S wave. But yeah, doing interferometry, looking at squids where you put the junction of one of the squids along different axes to maybe, so that you have different pairing gaps along. So there are tricks. Nobody's done them yet, and I think there's a lot of interesting work that can be done to understand what the pairing mechanism in STO is.
So how is this to pattern the surface by using, other gates? Imagine you want to construct the superconducting on a wire or a smaller quantum dot. Can you do this?
Sure. Patterning of these things is actually something we can, do very easily. You have STO, and what you do is, all you really need to do is put something on the surface that moves the ions up a bit, so that ions that reside on top of here don't couple as strongly as, say, these ions. So what we do for very big things is we do photoresist. But you can actually, we've done, there's a work that's published in APL where we've done this with E-beam lithography, and we can actually see coherent quantum phenomena, mesoscopic phenomena in these systems. And you can also do it by patterning the metal gates like I've shown. So you can definitely make a one-dimensional wire. It's relatively trivial from an experimental point of view.
In the middle of the talk, you were talking about the indium arsenide nanowire from the Delft group, and this has been around for a couple of years.
Yes. Yes.
Has this been repeated? I mean, every time I see
Yes.
somebody talk about this.
So a group from Weitzman did a similar experiment. It was published in Nature Physics, I think 3 to 6 months afterwards.
And they see the same thing? The extra peaks on the side?
They see, a similar thing. I guess the only very obvious difference between the two is that what you should see is as you open up the gap at k equals 0, you should see a collapse of the Majorana state to 0, and then as you further apply that magnetic field, actually the gap should open back up and close again. And so what you should see is a peak at 0. That peak should kind of open back up again and then close, and you can actually see that behavior a little bit better in the Weitzman work. And there's been a whole collection of work from a former student of Leo where they see a similar thing but ascribe it to unusual nature of the Andreev bound states in the system, not Majorana physics.
So is the feeling in the community that it may be Majorana physics, but it may not be, or it probably is, but it's just shadowed by some other effects?
I think the feeling in the physics in the community is that the physics of the theory is undeniable. Like if you do this right, Majoranas are there, and I don't think there's any question about it. We're split about half as far as the experimental goes, whether we've actually seen this state. That's the.
And your point was that this might not be the best system, actually.
Yeah, it turns out the real reason is that the spin-orbit interaction strength is just small. And we know, and this is what sets the energy scale associated with and that also sets the minimum disorder or minimum electron density you need to see these things. But
From my perspective,
it is, but there are things that are even so the relative energy scale for spin orbit in these systems is a Kelvin, roughly. There are other material systems, some that we've put forth in our new PFC renewal, where the spin orbit strength is room temperature, and so it can really dominate the energy scales that exist and move out. Just get Kondo out of the problem, get funny Andreev bound states out of the problem, and really see, if we made these systems, what do we see? And there shouldn't be any question about whether Majorana physics dominates or not.